This is my final independent study project in the RSGC ACES program, the BLDC motor controller. I'll also refer to it as an electronic speed controller, or ESC. And the reason I undertook this project was to continue what I started with my last ISP and create a BLDC motor pretty much from scratch. As you could see in that first clip, all the hardware functions well and the PCB works, but pretty flawlessly. However, I have not fully implemented my Hall sensor feedback system, which is why it looks janky at the moment. I should be able to fix the few remaining problems quite soon, however. So what is a BLDC or brushless DC motor, and why is a motor controller needed? All motors operate on the principle of converting electrical energy into mechanical energy. Just as a note that this is the opposite electromechanical conversion that an alternator makes, but both rely on the same principles of current, magnetic fields, and electromagnetic induction. BLDC motors eliminate the need for a mechanical commutator found in brushed DC motors by reversing the motor setup, where the windings are found in the stator and the permanent magnets are attached to the rotors. This is the final working prototype of the BLDC motor controller, and it brings many aspects of the ACES program together. The PCB took the majority of the time spent working on this project. It includes SMT components where available, all soldered with hot air in the DES. Furthermore, it does not use the auto router because of the importance of keeping traces quite short. Also, I used precise coordinates to place most of the components to make sure they were lined up symmetrically and looked aesthetic. I also used net classes to automatically set different trace thicknesses for each net in the design. And there are also many large copper areas, a large ground plane on top, and 3 different voltage source planes for V-in, 15 volts, and 5 volts on the back. The MOSFETs are also situated on the back for easier application of a heatsink. A full bridge configuration with 6 switches is implemented in the BLDC motor controller and consists of 3 pairs of IRF 530 MOSFETs connected to the 3 motor phases A, B, and C, as shown in the 3-phase full bridge diagram shown above. There is 1/2 bridge per phase. The sample circuit from the IR 2101 datasheet provides guidance on wiring, and I added some extra bells and whistles to make my MOSFETs safer and happier. The H-in and L-in signals of all 3 IR 2101s come directly from ATmega 328P. As mentioned earlier, the main benefit of BLDC motors is electronic commutation, as opposed to traditional commutation with brushes. And there are 3 control schemes for electronic commutation. Trapezoidal is what I'm using today, so it's the only one I'll talk about. And in the trapezoidal control scheme, the MOSFET bridge must switch in a specific sequence determined by the positions of the rotor's magnet pairs and the stator's windings. Depending on the direction of current going through the coil, a different direction of magnetic field is created in the stator. Each motor phase pair is energized by a positive or negative electric current in a specific sequence, and a 6-step commutation sequence is required to complete 1 electrical cycle in a 3-phase BLDC motor. The first 2 steps of a given sequence are shown in the diagram on the bottom left, and the phase currents in phase A, B, and C are shown in a diagram of trapezoidal commutation by microchip technology. I'll link this source in the description because I think it's really useful for understanding these concepts. In order to commutate efficiently and make this timing sequence kind of line up with the position of the rotor, I'm using Hall sensors. When a magnetic field is oriented relative to a sensor, as shown in the above diagram, the Hall sensor's digital output can be pulled low, and each output has a pull-up resistor on it, so really pulled high. And when the magnetic flux density is larger than the operate point, the output is switched on, and the output is state is held on until a magnetic flux density falls below BRP. And the values of BOP and BRP are shown in the table on the bottom left. And in the table at the top of the screen, there are different Hall sensor configurations for each output states of the phases. So in order to figure out the timing of the rotor and the, phases, I needed to determine the equilibrium position for each combination of the FETs in the full bridge. So right now A is sourcing current, so that's the green wire, and C is sinking current, so that's the yellow wire. And so we can see that this is the equilibrium position for that configuration. And now we can use that to determine the Hall sensor configuration. So Hall sensor B is high and Hall sensor A is high. Versatility with input voltages is quite important to the design of this ESC, and that's mainly because I can limit the current and the voltage will go down and it fluctuates. So I just need it to make sure that it stays at a steady 15 volts to make my MOSFET drivers happy. So I decided to reverse engineer a buck circuit that I had lying around my room and made it a fixed 15 volts by calculating the values of R2 and L1. And to do this, I just used equations provided in the LM2596 datasheet. So here's the code I wrote for this project. So the section on the left deals with the activation of the MOSFETs in the full bridge in order to determine the direction of current through the stator. And this function also deals with the speed at which the MCU cycles through the commutation steps using a potentiometer ADC reading. And then the section on the right sets up a pin change interrupts on the Hall sensor pins and outlines 6 different possible combinations of Hall sensor activation for, the commutation of the motor. Thank you so much for watching to the end.